Okay, well, good morning, everyone. Welcome to EECS 151 251A, Introduction to Digital Design and Integrated Circuit. We're coming to the 14th lecture of the semester, right? Exactly halfway into the semester, and we have learned a lot from, I guess, the high level thinking about digital abstraction, goes through like combinational and sequential logic, and also went through how we think about RISC-V design as a driving function for thinking about digital design. For the last couple of weeks, we have been navigating, I guess, the fundamental, the CMOS transistors and how we actually build more complex gates. And in particular, how we do actually timing analysis to think about how we can actually make our circuit run faster. And also we'll talk a little bit later, how also more efficient. So in today's lecture, we're going to introduce this really cool and also like fascinating concept of logical effort, which get to actually expand what we have discussed, again, mostly focusing on inverters, into other type of logic gates so that we can actually do more complex multi-stage path analysis and think about how we actually size our hardware. Before we get to our topic today, there has been actually a lot of interesting announcement from Intel. We mentioned when it comes to fabrication. When it comes to fabrication, we have like a couple very small number of actually leading fabs these days. We have Intel, and there's also TSMC, and we also mentioned Samsung is also a very major player in this space, right? More recently, Intel actually mentioned very good yield and very good result of their 18A process, right? 18A is like a little bit weird. We're introducing a new unit now, but fundamentally it's basically what I guess, typically we would talk about nanometer node, right? It's really just like 1.8, right? But 1.8 is really a bit awkward to say. So like, oh, let's use a new unit. So that's like become a integer. So it's really just like when we get to like 3, we talk about 7, 5, like we talk about 8, and 3, like Apple's latest process is this kind of weird variant of N3, but next node is basically N2, right? So Intel released their latest, I guess, N2 generation, equivalent to TSMC's N2 generation, and claimed to be actually fairly competitive in both power performance profile and also in yield, right? Which is very important when you think about the fabrication process. We did the yield analysis in, I guess, the first homework or so, right? So it's not only just about whether you can fabricate a few transistors or not, and also about whether you can mass produce. So Intel's latest result claimed to be like the 18A is actually in production, and it's in their actually called core series. We mentioned like the core generation. There are like a lot of different variations, but we mentioned it's basically start from Pentium Pro generation. So after Pentium Pro, with Intel tries the Pentium 4, which is extremely deep pipeline design and run into the power problem. And back after that, a lot of the design revert back to the Pentium Pro generation, which is basically the first Intel auto order execution. So after that, the main CPU line is basically the core line. And this 18A process is actually used to fabricate Intel's own CPU and get fairly competitive yield that's being released more recently. So we'll need to see, wait until when we get the real hardware and see how it performs. We mentioned briefly when we get to the CMOS transistor technology. In particular, for 18A, they introduced 2 most important features compared to FinFET. The first one is ribbon FET, where we talk about FinFET. You have a fin out of your transistor. Right now, you have like better control of the gate. Not only have a fin, you have this kind of, other people call this nano sheet, like this gate all around panels here or ribbons to actually get better contact area. And in addition, is it also power via, you may also hear people say backside power delivery. The idea is basically, traditionally, when you think about the metal layer, it has both power and a signal, right? For folks in the ASIC lab, you folks are seeing a little bit more metal layer and how the signals are routed on top of the transistor very bottom, right? There are layers and metals. And here the innovation is like separating signals and power. So actually the signals actually go, I guess, above the transistors, and the power delivery go actually beneath the transistor. With this, you can actually get like better density, so that you can actually separate the power and the signal metal layers, and you can also leverage both sides, right? But it definitely adds a lot more complexity in the fabrication process. So that's a lot of earlier discussion on the yield challenges, right? So it's really cool to see new innovations still happening in the fabrication process. And another very important part of having multiple players instead of getting this monopoly is that whenever there's competition, people will fight for new ideas and think about how they can actually materialize the new ideas to make their product more competitive, right? So it's interesting to see there's still pretty competitive different proposals being proposed, and people are actually trying different components to get better density and a better power and performance profile. So far it's just an announcement. I guess we'll see when the hardware is released for the Core Ultra generation, and to see where things are. But a lot of excitement in, I guess, the latest fabrication technology when actually approaching to very tiny, I guess, a few atom technology generations. So with that in mind, let's do a quick review of what we covered last week. We mentioned we start discussing the delay of inverters, right? We mentioned the inverter delay that can be characterized as a RC circuit to think about the propagation delay. And we introduce this kind of tau inverter as a time constant for unit size inverters. In this case, we can actually write the delay of the inverter, normalized delay of inverter, into two components. One is parasitic delay, which is a constant here. Another is effort delay, right? Effort delay is basically how big of load I'm driving, right? I have certain strengths, depends on how big the load I'm driving. That also dictates overall delay of my inverter. Well, once we have the mechanism to analyze a single inverter delay, we can start looking into more complex circuit. So here we're using, so far without introducing other gates, we're using this chain of inverter as our driving circuit, right? So here we can write our path delay. We can analyze our path delay. It's basically the sum of the delay of each stage of inverter here, right? So we can sum the delay together. And the path fan out is basically the overall fan out, the load I'm driving as an overall circuit compared to the input capacitance, right? In particular, when we think about a chain of gates, in particular chain of inverters, right? For each stage, right, the load I'm driving, let's say this is I stage, the fan out is basically the load for the I stage, the ratio between the load for the I stage and the input capacitance of the I stage, right? So here, one important component is the load I'm driving for this stage. It's basically driving the inverter of the next stage, right? Because we have a chain of inverter. So in this case, my load is basically the input capacitance of the next stage, right? Because now when we actually chain the inverter together, when I'm driving the input capacitance of the next stage, and this is my fan out. It's basically the input capacitance, my next stage, compared to my own capacitance. That's basically the fan out. Right, we mentioned overall, when we do circuit analysis, we want to minimize the overall path delay, right? So here is the delay of the entire path. We want our circuit to typically run faster, right, before we introduce energy, right? So what we want to do is that we want to size our inverter, which is, again, a very important parameter in the circuit design process, so that we can minimize the delay. Right, we discussed, I think Connor mentioned last time, right, when we have the chain of inverter, we have chain of inverter, we have like the product, which is basically the fan out of the entire chain is fixed, right, which is basically the overall load capacitance divided by the input capacitance, right? So we have the product of the term is fixed. I want to minimize the sum, right? We want to, the sum of the term want to be minimized. And that happens when basically every inverter stage has the same delay, right? We want to distribute the multiplied product into each stage. So in this case, for each fan out of each stage is basically nth root of the entire fan out of the path. With that, we can actually go back to our fan out, and we can start either go forward from the first input or go backward from the load to start assigning the inverters at each stage. Right, so this is basically how we start from IC analysis. We understand the delay of single gate, and then we can expand it to the delay of the chain of gates. And again, so far it's only inverters to think about how we actually minimize the delay. So in today's lecture, we're going to talk about how we can actually generalize the optimization, the step-by-step optimization we did, so that it doesn't only apply to the inverter, but also apply to other complex gates that are also of interest, right? So in this discussion, it's going to be interesting to think about what are the fundamental difference of the complex gate, especially from their topology compared to inverters, and how that impacts the delay analysis, and how we can use this kind of first order approximation to think about delay optimization. So that will be the lecture today. We'll talk about the logical effort concept. Again, this is a concept people introduce to make it easier to do first order approximation for actually a chain of delay with more complex gates. We'll talk about how we calculate that. And after that, we'll talk about how we actually extend our, again, inverter chain analysis into this kind of multi-stage network that can be composed with inverters, but also other complex gates, and how we actually do the delay optimization. So with that in mind, let's again just quickly review some of the fundamentals that will come in handy when we do actually more complex circuit analysis. When we talk about resistance of the material, right? It has a couple factors related to the overall resistance, right? Again, it's related to the material of the resistivity of the material, right? Different material have different intrinsic behavior that lead to different resistivity. That's actually very material dependent. Other than that, the overall resistance is very dependent on the dimension, right? We talk about, when we think about resistor, we have a couple parameters to modulate. We have the overall length, how long my resistor is, and typically the longer my resistor is, the higher the resistance, right? Because like runs longer, it has like more resistance overall. So the longer the length, the higher the resistance. And another set parameter is basically the cross-section area, right? Involves both the depth of the material and also the width of the metal or material, right? So far, we're focusing on the width, right? Again, the wider the weight we have, the bigger the cross-section area is, the easier the current can flow through, so the lower the overall resistance is, right? So when we have higher, wider the resistors, it actually have lower resistance, the overall resistance, right? So this is a very important dimension of the parameters when we think about different things that designers can control. So now let's back into the fundamentals, how we connect different resistors together, right? We talk about so far only inverter. Inverter is the simplest one. For both pull up and the pull down network, there is only one transistor there, right? Either PMOS or NMOS. Whenever we start to introduce more complex gate with multiple input, right? There's always more complex behavior going on. In particular, we'll see certain transistors being connected in series and certain transistors being connected in parallel, right? Again, just a quick review. When we actually connect two resistors together in series, the overall resistance increase, right? Double, right? We have higher resistance. It's similar to we have like a longer resistor now, right? So in this case, let's assume a fixed voltage. And remember, current is voltage divided by resistance, right? So when we increase, when we get an overall increased resistance, the current actually decrease, right? Think about the current is actually the driving function when we charge and discharge our circuit, right? When current decrease, our circuit get slower, right? It takes longer to charge and discharge our circuit. So we also see sometimes it's weaker. It's not as good at driving the load, right? The strength is weaker, right? Because it's actually the current is smaller. And when we actually put things in parallel, right? So now if you think about the current actually flows through this, right? The overall resistance is actually decreased, right? Again, so the current can go through this path and this path, right? The current actually increased, right? Because now we have parallel paths, right? Again, for this scenario, we have smaller resistance, we have higher current, we have a stronger circuit or stronger gate that's better at driving and charging and discharging the downstream gate, right? Make sense? Just a quick review. And you will see those concepts are very useful when we actually think about more complex gate. So let's take a look at what will happen when you get to more complex gate. We mentioned earlier, it's really cool to have inverter as a driving example because it's basically a single input, right? For either the pull-up network or the pull-down network, there's only one transistor in our path, right? So now let's say when we actually get multiple input, right? When we have multiple input, here is an example. What is the output of this gate? What does this gate represent? This might be a little bit annoying to see, but you can basically think of this as being connected here. So when we talk about when we actually write the output of a CMOS gate, we can look at a convenient way to have the pull down path where we add a bar here because the signals are inverted, right? For pull down path, we have A and B. A and B NMOS are connected in series, right? So this means we're building what gate we're building? NAND gate, right? Because A and B are connected in series, right? So this is a NAND 2 gate, right? Makes sense, right? Looking at the output. So we're building a NAND gate, right? So in this example, you will look at, again, the pull down path, right? We're having two NMOS transistors connected in series, right? We mentioned earlier, with the inverters, there's nothing connected in series, right? It's always drive, typically for the same sized transistor, it drives the load the best because nothing is connected in series, there's only one thing, right? Whenever we get to actually more complex gate, we have multiple inputs. There's always some of the transistors are connected in series, right? This is not related to even the sizing. We haven't talked about the sizing. It's purely about the topology, right? Just by when we have multiple inputs and the way pull up and pull down network constructed, there will be some of the transistors are connected in series, which typically make it poor or worse at driving the downstream current compared to the inverters. We'll talk a little bit more how we quantify that, right? But you see when we look at the topology, whenever we start introducing multi-input gates, right? Those actually make this typically weaker compared to the same sized inverter because now we have a couple transistors or even a handful of transistors actually connected in series, right? So this is purely the topology of the design, and we'll see how that actually lead to a more challenging design. Adam.
So when it's pulling down, it's weaker. When it's pulling up, it's got two in parallel, so it's going to be stronger, right? So when we say a gate is weak, do we mean that like whichever of the two directions is weaker is weakest?
Yeah, we are typically looking at the slowest path, right? You think about whenever we do circuit analysis, right? Even we'll talk a little bit later, even we'll look at pull up path, there could be a different scenario, right? You can have like maybe one signal is pulling up the circuit, or you will have like multiple signals are pulling up together, right? Whenever we do circuit analysis, we're looking at the slowest path, right? Because we want to make sure even the slowest path also work, right? So here we're looking at the slowest path. The slowest path is basically whenever things are connected in series and how we actually factor that. And logical effort, which is a pretty cool concept introduced as, again, a first order approximation to do circuit analysis, is a way to approximate this effect that purely based on the topology. Whenever we introduce more inputs, more things are connected in series, and that leads to a weaker, again, compared to a unit size inverter, a weaker topology, and that requires like special care whenever we think about the delay. So here is like the high level motivation. Again, one thing to keep in mind, we're looking at when things are connected in series and how we can actually optimize that. So how we actually put things together, right? So let's actually back to our the delay formulation that we had before and start thinking about how we actually extend this to more complex gate. So far, we have been looking at, again, the inverter delay, right? An inverter delay we mentioned, it's actually pretty useful to introduce this tau constant. It is size independent. It's the RC of the unit size inverter that represents the process, the intrinsic behavior of different process generation. And we can partition this, again, we mentioned this is like the parasitic delay, right? The intrinsically delay that we need to charge and discharge a parasitic capacitor as part of the gate. And this is a fan out delay, right? This is related to how big of load I'm driving compared to my own stress, right? So now let's see for the other gate, right? We mentioned as a very, again, first order approximation, right? We're basically doing this RC analysis for the more complex gate, right? Again, similarly, we have the behavior that we need to charge and discharge my intrinsic parasitic capacitance, and we also need to think about how we drive the load downstream. Right, we saw how powerful it is to have this kind of simplified, normalized delay, and they make it easier for our circuit, like circuit optimization for inverter chain. And we like to see that happening also for this kind of more complex gate. Right, so we write down the behavior. Again, we're looking at a particular gate, right? We like to see what is a normalized delay, again, normalized to the unit size inverter, right? So this is the delay. It's basically delay of my propagation delay of my current gate. Normalized to the unit size inverter, right? We can cancel this annoying 2 term out, and then what we basically have is basically equivalent resistance of my gate and the parasitic capacitance of my gate. I'm just copying the equations now, and the load, right? This is my propagation delay of my gate normalized to, we mentioned earlier, the RC constant of my inverter, right? The equivalent resistance of my inverter with the capacitance of the inverter, right? I remember we discussed before, we have the gamma factor as a ratio between input capacitance and parasitic capacitance, and for simplicity, we just say they are roughly the same, and typically they're like between 1 and 2. We just say they are roughly the same when we think about the ratio between parasitic and input. So with this, we can start actually separating the term, right? We have a plus term. We're adding 2 components together. Again, one is more related to the intrinsic parasitic delay, the other is related to the load, right? So the first term, again, just a simple rewrite, we have the gate resistance and the parasitic capacitance of my gate can be normalized to the RC term of my inverter. And I'm replacing this inverter back to the parasitic of my inverter, since they're the same, right? So with this, and then we'll talk about the second term later, right? So if you look at the first term, right, we're basically looking at the RC constant or RC term for the parasitic part, right? The parasitic delay of my multi-input gate normalized to the parasitic delay of my unit-sized inverter. And we'll use this as a parasitic We'll call this again as our parasitic delay. We'll talk a little bit more how we calculate this, but this is again the parasitic part of my delay, right? Very similar to the inverter, but not the inverter is simply one because everything is normalized to inverter, but now I have a more complex gate, right? So this is the first term. Let's look at the second term, right? The second term, if we, again, the resistance of my gate with my load, again, with the RC of my inverter, right? So this is, again, just a simple rewrite. We split the term. Before the first part we already talked about, it's a parasitic delay, right? How about the second part? The second part so far is still combine the load together. Remember we talked about fan out, right? It's actually easier if we think about the load. When I fan out the load I'm driving compared to my own stress, right? So I'm going to do a rewrite where I separate my load out. So I have a similar term. Let's say my capacitance, my input capacitance of my gate. So this get to a similar term because we have the ratio between the load and my input capacitance. And I'll rewrite this as, again, my gate resistance. I'm adding this input capacitor on my gate and keeping everything the same. Inverter and the capacitor. So I'm adding this term on both sides. It will cancel out, but it gives me this nice way of, again, thinking about this is the same fan out term, right? Again, the ratio, I like to think about the ratio of the load I'm driving compared to my own strength, right? So I still have my fan out term. And this, we'll talk a little bit more. This is basically what we call logical effort. The effort to drive the logic function that is independent of the sizing, that's independent of the load, that's just the intrinsic property of the topology, right? So that's why it's a logical, right? It's all about the logical expression, and just by the fact that we're having more inputs that lead to a different stress compared to the inverter case. And this is what people call logical effort. And you get this very similar term where you have a parasitic component, you have a fan out component, but the fan out component have a special weight. And this weighting function is basically the topology complexity of the gate. So far makes sense how we actually go through that and using the same term to actually have this structure where we have something very similar to this, but now we're adding this weighting function called logical effort before our fan out. So this is, you'll see the same derivation in the next slide. So you will go back to this more simpler version where we have our delay following the very similar. When we have the delay of inverter, we mentioned earlier, it's basically 1 plus F. It's the same. We have the parasitic portion and also the effort delay, right? Before the effort delay is just the fan out, but now we mentioned earlier, we want to factor in, now because we have multiple inputs, this intrinsic property or the topology of the gate, add another weighting function. And this is a logical effort that we are using, again, as a way to do the first order approximation for the analysis, right? Again, we mentioned earlier, as an inverter, the logical effort of the inverter is 1, right? Because it has the same RC constant, it has the same topology, right? So like in this case, the inverter delay will just be a special case of the logical effort delay for more complex gate, because inverter, the logical effort is 1. Right, so this is basically how we use like introducing another factor, again, describing the intrinsic property of the topology of the gate and how that can assist us to actually analyze more complex gate using very similar first order approximation that we have been using for our inverter analysis. So how do we actually get the logical effort, right? We mentioned the logical effort is basically model the intrinsic property, and as a way to quantify how much weaker really my gate is in terms of actually driving this, delivering the same current, right? So here we're basically finding the normalized ratio compared to an inverter. How much weaker is my current gate, right? Because from the topology, something is connected in series and it is weaker than inverter, right? There are multiple ways to calculate this. You see, we're basically having two parameters, the RC parameters, our circuit. You can either fix R to get the ratio of C, which is what we are doing here. You can also do another way where you fix C and see how much weaker we mentioned earlier the current is. Either is the same, you can actually do it offline. I find it easier to think about we actually fix R because we want to deliver the same current and see how much actual effort we need to actually compensate to deliver the same effort. But you will actually get to the same conclusion. In particular, we mentioned at a very high level, we basically want to fix the current, right? And fix the current, we basically get the fix the current in terms I want to deliver the same current compared to my unit-sized inverter, right? We want to deliver the same current, right? So with the same current, we need to have the same resistance, right? With the same resistance, we mentioned we need to manipulate the weights of my transistors so that it can, like something is connected in series now, right? My resistance, if I don't control it, it will grow bigger, grow larger. But now I need to deliver the same current, right? We need to size the transistors to make my resistance go smaller, and we need to see the ratio again. So we fixed this, we want to see the ratio of my input capacitance. And that gives us an idea of how much more effort, how much bigger my transistor need to be to deliver the same current. Does that make sense? The intention of this effort, we want to get to the same current, right? Then we get the same resistance, and we need to see how much bigger my capacitor need to be, and that give us a logical effort. It's a little bit abstract. We'll see a couple of examples. Hopefully that help you understand. This is, again, we want to factor in some components are connected in series. If we don't do anything, the current will drop because we have higher resistance. Now we are going to make an effort, right? Make the effort to compensate the topology, the logical property of my gate, and how big that effort is, right? So in this case, what we basically do practically, we basically size the transistor so that my equivalent resistance of my gate is the same as a unit size inverter. Once my resistance is the same, it basically means current is also the same, right? With the same current, I have the same stress, but now I need to figure out how much actual effort I actually did to compensate my design to actually achieve the same current. And that compensation factor is basically the logical effort. Making sense so far? At a very high level, we'll see how it works in action, but that's basically the compensation we're doing to calculate both and this applies for both logical effort and also the parasitic effort. Again, we size it so that current stays the same, and we will see the ratio with both the input capacitance and the parasitic capacitance. That give you us a factor to see the normalized parasitic delay and also the logical effort. So far, so good. I guess it's a little bit abstract, but we see the intuition behind it, what we're trying to do. Let's take a look at some example to make it less abstract. Okay, so we mentioned earlier, this is our NAND to gate, right? We have. So here we start with our inverter. It's unit size inverter, we just size both NMOS and PMOS of size 1 here. And we want to figure out what are the logical effort for, we mentioned logical effort of my when we get to 2 inputs, right? Something we mentioned earlier here, if you look at the pull down path, right? 2 NMOS transistors are connected in series, right? We want to see how, what's the implications for this topology. We mentioned earlier for logical effort, we basically size the width of my transistor so that they have the same R. Again, with the same R, it's the same current. And then I can actually do the ratio between my input capacitance of my current gate with the input capacitance of my unit-sized inverter. Right. So let's take a look at what's the ratio. So let's first look at what's the input capacitance of my inverter. So now we only have a single input, which is A. This input is connected to two gate capacitors, right? One for the NMOS gate and one for the PMOS gate, right? So the input capacitance, we'll look from the input, is basically, we talked earlier, size of, like sum of both the PMOS gate capacitance and NMOS gate capacitance. Everything sized at 1 here. So the input gate capacitance of my input. So input capacitance is the sum of the gate capacitance. It's just 2 in this discussion. Does that make sense for the input capacitance of the inverter? Okay, so now let's look at, now we have two inputs, right? Let's look at the B input, which is easier, right? So before we do that, we mentioned the step we're taking is that we need to first size my transistors, right? Again, we want to have the same current, right? So now we mentioned everything in input in my inverter is size 1, right? And the things get weaker whenever we have transistors connected in series, right? So we mentioned the slowest path. So let's look at the slowest path here, right? So now we have 2 transistors, one for input B and one for input A that connected in series. And now, but I want to deliver the same current. So this is I1 and this is I2, right? So I want to have my I2 the same as R1, right? So I want the same current. I want to drive the same current. How should I size the resistor? How should I size the transistor here? The same? The ratio, which ratio is the same? Let's say we're only modulating the width, right? So we're only modulating the width. So before, let's say this is 1 here, right? So we look at the pull down path. We want to deliver the same current. So let's say we have 2 RB and RA. Let's say this is 1 and this equivalent resistor is R. So what should RA and RB be? So let's say RA and RB, we size them same. What's the relationship between R here compared to our inverter? So they should be the same as inverter here. So in this case, what's the overall resistance of my pull down path? So I have 2R here. What's overall? Any? So my overall resistance of my pull down network is RA plus RB, right? So now I want the current going through RA and RB the same as the current going through my inverter. Should the A and B resistors higher or smaller than the resistor of the inverter? Smaller, right? Because I have 2 things connected in series now, right? So in this case, as what Annie mentioned, right, we want to deliver the same current. What we want to do is the sum of now my overall resistance is actually the same as what the resistance we had before, and that's how we get the same current, right? Does that part make sense? Right. So here we mentioned earlier, we want to size. We'll talk about how we size it later, but we want to have the same current. We want to have the same resistance. Again, now 2 things are connected in series, right? So now I actually want my resistance to be smaller so that the sum of that is the same as what we had before.
In these kind of circuits, do we care if like all the transistors are in the saturated region or like the linear, or like it doesn't matter?
we move on from that abstraction now. So we talk about charging and discharging that's related to R. We'll just look at the steady state and how the current is actually work overall. Yes. So far makes sense, right? So now if we actually, let's also assume their size the same, we actually want to have each of them to be much smaller, right? And we talk about, so we have our, in this case, the same, they are actually, let's say they have the same resistance and they will be half of the original resistance to actually achieve the same current, right? So we want the resistance of each transistor to be half of the original resistance. So have resistance to be smaller, it means my transistor to be wider or narrower? Equal? Wider, right? The W controls the cross section, right? So here we basically want to make the resistance wider, the transistor wider to deliver smaller resistance, right? So now we actually think about, if I can actually change. Change a different color here. So I actually want to size this, double the size to have actually bigger transistors to actually deliver the same current, right? So that's my pull down network, right? We're looking at the same current. To have the same current, I actually want to size my NMOS transistor bigger because they are connected in series part. So now let's look at the, let me change another color. Let's look at the pull-up network. So now for pull-up network, it's a little bit different now, right? Pull-up network, we don't have anything connected in series, right? The pull-up network is a dual of the pull-down network. So we have two PMOS transistors connected in parallel, right? So what's the worst case? What's the slowest condition for the pull-up network? Just the one resistor, I guess, just like, so if we think about this, right? We have two resistors here, right? The fastest is like when both of the parallel paths are on, right? We're charging both of them through the two paths, right? That's the fastest one. The slowest one is just, let's say, just one of the transistors is on. It's either through A or B is on. So I'm going through one pass. So this is the slowest pass when we think about pull up. And this slowest pass is actually the same as the inverter, right? Which only have a single transistor there. So the fastest pass is even faster than the unit size inverter, but the slowest pass is actually the same as a unit size inverter, right? Because it only has one transistor there, right? So if we say the pull up pass, we size PMOS as a unit size of 1 to have actually the same current. The PMOS for my NAND gate is, what's the size of the PMOS on my NAND gate? It's also 1 because it's the same, right? The slowest pass is actually the same as the pull up here. So we also size the pull up pass, the PMOS, both are size 1. Does things make sense so far? How we actually size that things for pull down and pull up to deliver the same current? So now we talk about the first part is the size, right? After the first pass, things get easier, right? After that, we just calculate the logical effort. Again, the logical effort is a ratio of my input capacitance, right? Let's again look at from one of the input B here. What is the input capacitance? Here we mentioned the PMOS is size 1, NMOS is size 2. So what's the input capacitance? Let's see from node B. Well, if I look through the input, what's my input signal connected at?
Sorry, question. Why are the pull-up transistors not size 1?
Oh, well, so we mentioned we're optimizing for the worst case.
Yes.
And the worst case is,
Pulling down.
well, that's between pulling down and pulling up. But when we look at the pull up, when is the worst case? What conditions I'm pulling up?
Oh, if only one of them is on, yeah.
Exactly. So we're sizing the worst case. Okay, so now we're looking at from B, how many, what's the input capacity, overall input capacitance that we're seeing from input B? It's the size 2 gate capacitance from the NMOS and also the size 1 gate capacitance from the PMOS, right? So the input capacitance is 3, right? We can also do that for A, it's the same, it's also 3. Does that make sense? This? Right, so if I look from this node, the gate capacitance I'm connected to the NMOS is size 2, right? Size 2 is basically normalized. The input capacitance is 2, so this is my NMOS part. And we look at my, each input is connected to both input, NMOS and PMOS, right? So look at the PMOS, we mentioned it's size 1, so this is a PMOS part. And like the capacitors, I'm charging and discharging both capacitors there, right? So we sum those two together, and that's my input capacitance.
Are those numbers describing the bits of the transistor, right?
Yes.
How are you going from just directly to the capacitor?
Oh, that's a good question. We didn't cover that. So if you think about, I guess, capacitors, like we have capacitors here. I guess this is the length. This is width, right? And we think about gate is also a capacitor, right? So for resistors, we mentioned when it gets wider, the resistance gets smaller. For capacitance, when my metal gets wider, my capacitance get bigger, right? It's proportional to my area. So that's a connection I guess we didn't make. The size is also proportional to the capacitance, right? When you get a wider gate, you actually get a bigger capacitance, right? So that's the effort we're doing. So we get input capacitance is 3. So we do 3 is my input capacitance of my gate. And we look at the inverter, we have the input capacitance of the inverter is 2. So now the normalized logical effort is 3/2, which is basic, again, quantifies the additional effort I'm doing purely by the topology of the gate. Brendan.
So when we're talking about the input capacitance, we only care about the max of any input. We don't care about, there's no like combined effect of like adding the input of A capacitance plus the input of B capacitance.
Oh, that's a good question. So when we think about signals I'm driving, A and B are different signals, right? A could be coming from somewhere, B could be actually also coming from somewhere, right? From a signal point of view, if I'm A, I'm thinking about the input I'm driving, the capacitance I'm driving, right? So this is to a particular input, yes. So this is to a particular, for this particular input, what's the implications of the gate here? One more question. Where is the capacitance of? Oh, so we mentioned NMOS is sized of width 2, and we mentioned when width get wider, capacitance also get wider, get bigger. So this 2 is from the NMOS. Right. Again, we mentioned earlier. So here we're looking at for each input, either input A or B, right? So this looking at I'm the signal, I'm the B signal. I'm looking at how much I'm driving as one of the input here. So now I'm not adding all the different components together. So this is per. So logical effort is also per input. So here I'm looking at in terms of signal I'm driving as one of the input and how big I'm driving here. Okay, so this is like what we did. It's a little bit messy of the annotation, but this is basically the thought process we did for logical effort. We can also do the same thing. Let me try to have a different color. We can also do the same thing. We mentioned the parasitic effort, right? We can also do, again, the parasitic of the gate, divide the normalized with the parasitic of the inverter. right? And when we do this, again, crude first order approximation, we look at the parasitic capacitance. We typically look at from the output side. So before we're looking at the input, right? Now we're looking at the output. So we're looking at from the output side, what are the different drain capacitance that we are charging and discharging, right? That's the parasitic capacitance that we're seeing here. So here, again, we have the, I guess, the drain capacitance for both PMOS and NMOS. Those are the two things we're driving. And when it's sized at 1, the parasitic capacitance is basically both PMOS side and NMOS side is basically 2 here. We're driving, we have 2. Again, one from the PMOS, one from NMOS. That's a parasitic side. And you can do the same thing again from the output. Whenever we talk about parasitic, is look at how much, what are the capacitance that we see from the output. That's the parasitic capacitance that we're driving, right? So from the output, what are the transistors that are connected to the output? It's this transistor here, this PMOS, this PMOS. Both PMOSs are directly connected to output, right? For NMOS, it's only the one on the top connected to the output, right? Because the one at the bottom is not connected. So as again, first order approximation, you can actually just look at from the output and see one parasitic capacitors here, another one here, and another one here. Does this part make sense? What are the drain capacitance seen from the output as a parasitic? It's basically which node. This is connect to one PMOS, another PMOS, and another NMOS. Right? That's a connection so far. Right? And again, the capacitance is proportional to the width. So we have 1 for PMOS, another one also for PMOS, and then 2 for NMOS. That's the parasitic capacitance that we're seeing on the case. Question there? When we talk about the drain capacitance, does it matter which part of the circuit it's on? That's a good question. Well, when you think about things need to be charged and discharged, right? All the drain capacitance, one side is a ground, the other side is output, right? But whenever output switches, the capacitor need to be charged and discharged, right? So in that case, it's like this drain capacity, it doesn't even matter whether the circuit is on or off. Those are actually directly connected to the output node, right? It's connected to the drain node, right? So so it doesn't really matter whether the circuit is on or off. It's basically what are the drain capacitance are connected to the off. If you actually do more, we'll talk a little bit more of actually how you use Elmore delay to do this kind of fine-grained analysis. Then we'll actually have different paths there. But for this first order approximation, you basically look at the drain node and look at all the drain capacitance that's connected to the output. There's one question here.
So the A transistor in series has any impact on the drain capacitance? Is that just because it's an approximation, or?
Yeah, so it still have the drain capacitance here, right? It's become an internal node. It's not directly connected to the output node. So again, this is a first order approximation. You can actually use Elmore delay to actually write down the different paths. But for this approximation, we only look at the drain node. But yeah, there is also, it just has the drain capacitance become an internal capacitance. Yeah. So in this case, so that's also how we get the normalized parasitic delay. I need to move on. We can come back to more questions, but you get the high-level idea of the steps that we're doing here. Okay, so this is, I guess, a simplified version. That's all the exercise we did before, looking at the input, looking at the parasitic, and we can actually calculate the logical effort and the parasitic effort here. Well, again, you can actually do things actually pretty similar to the NOR gate. Before we talk about NAND gate, you can actually do the same thing for the NOR gate. Let me switch back to the NOR gate. And here, when we look at the NOR gate, instead of NMOS connected in series, what has changed is that when we look at the NOR gate, now PMOS connected in series, right? We can actually, the same analysis applied here. Whenever things are connected in series, they are weaker to compensate we actually need to make them bigger so that they can be stronger, right? So here we also want to size the PMOS to be bigger so that to compensate they're actually connected in series. And for NMOS, it's the same. It's the worst case is either of the pass on, which is the same as an inverter case. So here we can actually also size our NOR gate, which is a dual of the NAND gate. And here we can also, in this case, the input capacitance seen from the input side is still 3. The parasitic, again, looking at things connected to output, is still 4, right? So we see the same logical effort of NOR gate is, again, the same 3/2, and the parasitic is 4/2. We'll go through this relatively quickly, but you can actually do this offline to also go through the exercise. So I guess we'll talk a little bit more. So far, we talked about the logical effort and how we can actually get the logical effort by doing the gate analysis, topology analysis, and citing that to have the same stress to get actually the logical effort for different complex gate. Next, we're going to talk about how we actually do the delay optimization, the multi-stage delay optimization that we did with inverter chain, but this time with more complex gate. Before we get there, a couple announcements. Midterm is next Tuesday, a week from today. The scope will be the content we covered by last Thursday. So today's lecture is not not in scope for midterm, but this is very important. So I definitely encourage you to review the material. So it's basically up to the inverter chain delay that we covered by Thursday. We'll have the logistic is already announced on it. We'll have midterm review during discussion this week. So this week we'll recap the inverter chain delay that was not covered in discussion, and we'll go through some of the past midterm exercise.
By one page note, you mean like one side only?
By one page note, it's one page, you can go both sides. Okay. Yes. Double side, yes. And no need to write anything. RISC-V green card related, RISC-V green card will be provided. And what's that? It doesn't have to be. If you prefer printed, it's also fine. Yes. It's one page note. And I guess we discussed earlier, project checkpoint 1 due this Friday. Again, very important. It's light in terms of workload, but very important for your project. So definitely spend time working on that. For folks who haven't finished the lab, definitely use this week to actually catch up the lab because things will get intensified really quickly. Before I move on, any questions, thoughts? Okay, well, stay tuned on ad. If we have any announcement, and we'll post them on ad. Okay, so far we talk about the logical effort. Again, how we like to use this to represent the intrinsic topology of the gate. Again, compared to the inverter, and we discussed how we actually calculate logical effort for more complex gate. The intention is always use this method to actually optimize multi-stage network, right? We did a little bit that for the inverter chain, and now we're going to see a little bit more of how that can come together when we actually think about more complex network. So just to get things started, a very simple example, right? So now we talk about when we have actually more complex circuit, right? And now we like to work on the delay of my inverter, right? So here, my inverter is driving 4 unit-sized inverter here, right? So all the inverter here, you can think about there of size 1, right? So we discussed, we can actually think about the delay, which when we actually introduce a concept of logical effort is basically the parasitic delay intrinsic to the gate, and then instead of just fan out, it's actually the logical weighted by the logical effort, right? For this example, is actually pretty straightforward, right? Because the inverter, the logical effort of inverter is is 1, right? There's nothing connected in series, right? Everything is normalized to inverter. So the logical effort of inverter is 1. For the fan out effort, right? For what my inverter here is driving, I'm driving for the same size inverter, right? So here my fan out, my load is 4 compared to my own size, right? So my fan out is 4, right? I'm driving 4x of my own capacitance. And my parasitic delay, again, for inverter is normalized to inverter, right? It's also 1, right? So here, when we think about the delay, its logical effort is 1. Fan out effort is 4 plus 1, right? So this is a very straightforward way of thinking about how we think about the delay. And this is what we covered. This is, I guess, a more well-written version. So just to recap, right? Last lecture, we talked about once we get this kind of very normalized delay of the two component, we can actually start optimizing more complex circuit with multiple gates, right? In particular, what we leverage is to, again, we want to minimize overall delay, which is basically sum of the delay of individual stage. And in particular, we like to minimize the delay, right? Minimize the delay of the entire chain. And the minimize optimal point is basically to fully distribute the fan out to each stage, right? We have the overall fan out is basically the load I'm driving compared to the input capacitance of the first gate, and the delay is basically minimized, we mentioned earlier, to actually fully equally distribute my own overall fan out effort to all the individual stage. And that's how we get the fan out for individual stage. And once we have the fan out for the individual stage, we can, as we reviewed earlier, we can actually start thinking about the size of the transistor for each stage, right? We can do something pretty similar to actually what we did with inverter chain, but now actually factor in, we can consider more complex gates. So now we're doing actually something pretty similar. It's, again, multi-stage networks, right? So we have multiple stage now, and we like to figure out how we actually optimize to actually get the optimal delay, right? Again, the overall delay, what we had before, right, is we mentioned for each stage, delay is basically parasitic times logical effort multiplies by fan out, right? So this is, again, we talk about single gate, and then when we look at the entire path, we basically sum every stage together, right? Here we can use, there are different terms for it. Basically, this weighted fan out, right? So instead of just fan out as it is, we're weighting it using the logical effort because different gates adding a different layer of complexity, right? So here you see people call it stage effort because it's talk about the overall effort of this particular stage. You also hear people, I guess sometimes people call effective fan out. Fan out, because now it's like fan out but being weighted, right? So this is like weighted or effective fan out of the stage, right? You hear people use different terms for it, but it's basically used to characterize this combined weighted term, right? Stage effort or effective effort, effective fan out, and the overall path effort, right? Again, we see this something very familiar. It's basically the product of the weighted effort of the entire path, right? We basically get the product of the weighted effort of the same path. Here are different terms that people are introducing. It's just like, again, like way of describing what it is. It's actually talking about very fundamental thing we had before. So you can also rewrite it with basically the overall path fan out. It's basically the load, the ratio between the load to my input capacitance, and overall, I guess, path logic of effort, because we're talking about the product, right? You can also put all the product of the logical effort together. That's basically the path logical effort. So far, we're not introducing any new concept. It's just a different terminology. So it's just what are the different terms people are using to do the approximation. But what we really want to do is to actually figure out how we can minimize overall delay, right? And as we discussed earlier, the same principle holds when the delay is minimized, when we actually equally distribute the overall effort to each stage, right? It's basically when each stage has the same effort, right? We mentioned the overall pass effort is basically the product of all the logical effort and find out effort of each stage, the product of the term, that's basically the pass effort. And the delay is minimized, where each stage is basically have the same, I guess, the overall pass effort, basically the nth root of the pass effort, right? We'll fully distribute the overall pass effort so that each stage has the same effort. Once we have this, we can actually do things very similar. We figure out what my stage effort is. We can actually know this is a delay I'm getting, right? When every stage actually have the same effort delay. So it's basically n time number of stage, and then we have the parasitic term, right? The sum of all the parasitic delay. And that will be the overall delay. And again, once we know the overall stage effort, we can actually start sizing the transistors because we know the logical effort, we know the gate, we know the logical effort, we know the overall effective effort, and we can start sizing the gate. So again, a little bit abstract, but we're basically walk through the same steps we did compared to the inverter chain, and that's the way how we actually optimize it. Let's take a look at an example. So here, different from what we have seen before, this is an example where we start introducing more complex gate, right? So it's not only just inverter. We still have two inverter here, but we are adding a NOR gate and also a two input NAND gate, right? And they are sized and X and Y, right? So as what we typically do, our intention is to minimize overall delay, right? We mentioned the delay is now for each stage is a parasitic of each stage as a logical effort times fan out effort, right? So with that, we'd like to understand what are the values for each gate, right? Let's do this together. Let's do the first inverter. The logical effort of inverter is 1, right? It's normalized to itself, right? The parasitic effort of the inverter is also 1, right? We're talking about inverters. The fan out of the inverter, we mentioned the second and the third gate are just use X and Y because we want to solve them in the end. So let's say the second inverter, second gate is size X. What is the fan out of the first inverter? What's the fan out? What's the fan out I'm driving here? X, right? It's X. So we mentioned the fan out is basically the downstream gate, right? So we're driving the downstream gate. You can actually X over 1 because my input, my first inverter is sized at 1 here. We can do the same thing. We have another inverter here. Again, logical effort is 1, parasitic effort is 1. The fan out here, I'm driving the load, right? For the last inverter is 36 over my size is Z, right? For the last inverter, right? So we are done with inverters. Let's take a look at our NOR gate. What's the logical effort of the NOR gate? Alberto? 3 over something, it's normalized, right? To inverter, what's an inverter? You have 2 equally sized, and then input capacitance is 2, right? So it's 3 over 2, right? Well, this will become very handy. We'll have seen this enough. The parasitic, you can also review your notes. It's basically 4 over 2. Look at from the output, normalized to the inverter. The fan out of this gate is Y over X, right? My own input capacitance is X. I'm driving. My next gate is size as Y, right? And you will see the same. Oh, now it's like still 3 over 2, 4 over 2, and for this one is Z over Y, right? So that's a fan out for the third gate. So we have I guess we talked a lot earlier, we have the term for all the 3 factors, right? So first, we talk about, we like to, whenever we think about design, we want to get the overall pass effort, right? What is the overall pass effort that we are doing, which is basically the product of logical effort for each stage and the fan out effort for each stage, right? That's the overall pass effort. You can do this one. There's multiple ways to do this. That's for this one, we can do pass logical effort and fan out the product of each individual logical effort and the fan out effort. And later you will see they all cancel out with each other. So you can, logical effort and fan out effort is z over y. Logical effort is 1. Fan out effort 36 over z. Right. So here we're basically writing, I guess, the product of all the stage logical effort and fan out effort together, and you will see those terms all cancel out with each other. Right. So now what we have is we have 2 here, and 9. So this is 81 when we actually multiply everything together. See how things cancel out, and we have very simple math there. So now we mentioned when we have overall pass effort, right? Here, n is 4, right? And the minimum delay achieved when we equally distribute my pass effort to every stage, right? So now the optimal stage effort here is basically the nth root of my pass effort, right? Or equally distribute that. Our pass effort is 81 and n is 4. We have 4 stage. So my stage effort is 3, right? So here is how we get our stage effort. We equally distribute, right? We have very nice number to play with. So we get our stage effort, right? So that's the most important part, right? Once we have that, we know what is the minimum delay. We also know how we actually size our transistors. Again, here is a note, right? So now when we actually know, we mentioned earlier, our optimal stage effort is 3, right? So we can actually know our delay at 4 stage is 3, and then we can add our parasitic delay together, right? So it's 1, 4 over 2, 4 over 2, and 1, right? So that's the sum of the parasitic delay and my stage delay, right? So this gives us the overall delay, right? So this is a minimum delay. We have one more step to go. So now we have the minimum delay calculated. And finally, we can actually size the gate now, right? So now because we know the stage effort is 3, and we mentioned earlier, stage effort is basically logical effort, and this is basically the fan out effort, right? The load of my output, the ratio between the load of my output of my input, right? Let's do a couple examples here, right? So for this, like our stage effort is 3 for my inverter. My logical effort is 1. It is an inverter. My fan out effort is 36 divided by Z. That's my fan out effort, right? Which basically means Z is 12. Make sense? Right, let's do a couple more. Let's look at the Y stage. Again, my stage effort is 3. It's distributed to the Y stage. My logical effort is 3 over 2. That's my logical effort. My fan out is Z over Y. Make sense? Right? And Z is 12. Right? Right? So this is 6. So Y is basically 6, right? We have 3 also cancel out. Y is 6. Make sense what we did? Okay, I guess as a homework, you folks can do the X, right? You can repeat this process with the stage effort. You have everything, actually all the terms here for the optimization you need. So you see what we did through this process. We basically repeat what we did was inverter chain, but now we have a little bit more powerful analysis that we are not limited to inverter chain. We can actually do the same analysis to more complex RC circuit with more complex gate. Again, a quick review. We talk about the logical effort. It's basically the ratio of the capacitors to deliver the same current, right? It's only depend on the topology, right? It's really as a way to measure or calculate in the internal topology complexity and to overcome that complexity. So that's the effort we're making to overcome the logical property, right? In practice, right, we can actually do the calculation to size a transistor, deliver the same current, so have the same resistance, and then we can actually calculate the logical effort and the normalized delay. With that, we can actually do the same optimization with the multi-stage network, now not limited to inverter, but also with more complex gate, and we can fully distribute the path effort to each individual stage. We get the minimum delay we want, and we can actually work either forward or backward to think about how big the transistor we need. So there's a lot in this lecture. I hope you find at least a symmetry with what we did with the inverter delay, but now with additional logical effort so that you have another mechanism to think about more complex gate. This lecture is not within scope for midterm, by the way. I do encourage you to review the material because there are like a couple components a little bit hard to understand. So while it's fresh, definitely review the material. We'll also have a homework to help you to understand the principles behind it, and it will be a 2-week homework, so it's only due after the midterm, right? So take some time to review the material. Great to see you all, and looking forward to more discussions.